The Zoom session is being brought to you by the Fractal Bullseye Bubble Fire. All right, for today we finish off chapter 4, which means that the chapter 4 we do homework we do next Monday. All right, 4.6 is about exponential and logarithmic models and measures, and 4.7 is about logarithmic scales. All right, now we start off with common enough thing, exponential growth. Where P is the initial population, P is P naught, P, no subscript, is future population, K is a growth rate, and T is the time in years. So P equals P naught e to the KT. It grows exponentially with a doubling time. Similarly here, P equals P naught 2 to the T over D, where D is a doubling time. You can convert this into this with an appropriate bit of logarithmic and exponential algebra. So D is a doubling time it takes for it to double in size. That's true for every exponential. There is a doubling time. Radioactive decay has a half-life. Here it's decaying away with a half-life of H. R equals R naught 2 to the negative T over H. R naught is the initial radioactivity. R is the later radioactivity. So after H years, the radioactivity halves. Okay. And if we have a doubling, P equals P naught e to the KT, we'll figure out the doubling time by setting P of D, doubling time equals twice P naught. Then plugging in P naught e to the KD equals 2 P naught. The P naughts cancel, so the doubling time does not matter what the initial value is. It's the same doubling time. So e to the KD equals 2, take a natural log, KD equals log 2. So doubling time D equals log 2 divided by K. So for example, if it's growing at a rate, if P is growing at a rate of 5%, so K equals 0.05, then the doubling time is ln2 over 0.05, which is 13.36, 13.86 doubling time. Okay, we have a cooling problem, Newton's law of cooling. If something starts out at temperature T, at time T, and it's cooling to TS, the surroundings, so it cools off. It's exponential decline to the surrounding temperature. So temperature at time T is the stable temperature, TS, plus D naught, a constant, times e to the negative KT for a positive constant K. And D naught is this difference between T of 0 and T sub S. So okay, the difference between the temperature of the cup of coffee and the room decays exponentially. If we can solve for e to the k, then given that we have some later time star, and this will be the temperature at time T will be the stable temperature plus T naught minus TS, that's a D, times this mess, the T over T star. And T equals T star log mess over K. Okay, whatever. For example, okay, Richter scale. Richter scale is a, okay, we talk about S, standard earthquake, and I, the intensity of the earthquake, measured in terms of displacement, measured by the seismograph, measured by 100 kilometers from the epicenter. And standard earthquake has a displacement 100 kilometers from the epicenter of 1 micron, 10 to the negative 6 meters. Richter magnitude is common log of I over S, the intensity divided by a standard intensity. And decibels are very similar. We have intensity of a sound in watts per square meter, and I naught is a standard intensity of 1 trillionth of a watt per square meter. And decibel measure, B, is 10 common log of I over I naught. So every time the intensity of the sound in watts per square meter goes up by a factor of 10, then the decibels increases by 10 points. pH scale. All right, here we have a hydrogen ion concentration. pH is natural, is minus the common log of hydrogen ion concentration. The minus was to make things positive numbers, so that 1 means 10 to the negative 1 concentration, and that's highly acidic. Whereas 13 is 10 to the negative 13th in concentration of hydrogen ion, and that's bitter or basic. Actually, now Although this is somewhat inaccurate, it's not H plus concentration. H plus is a proton, a subatomic particle. What happens in water is that it latches onto the nearest water molecule and get a H3O plus ion. Same difference. So, for example, a 10% growth rate makes what doubling time? Doubling time is natural log 2 over 0.10 is 6.93 years. A 2.6% doubling time, growth rate gives you what doubling time? Doubling time is natural log 2 over 0.026, 26.66 years. If you have a 3.5% growth rate and the initial value of population is 1.2 million, after 20 years, what's the population? Population is P naught e to the KT, 1.2 million times e to the power 0.035 times 20. Okay, after a bit of calculation is 2,460,503. I think the and 3 is a bit too much accuracy. Really, you only have one decimal place accuracy. So I say at best we can say 2,400,000 is the best you can do for accuracy. 32-year doubling time, P naught is 3.76 million. And after 100 years, what's P? All right, well, P equals P naught times 2 to the T over D. 3.76 million times 2 to the power of 100 years divided by the 32-year doubling time. After a bit of calculation, it's 32,802,472. Again, I would basically skip all the figures. I would give it only 3 figures of accuracy because this is all that has. So thorium-227 has a half-life of 18.4 days. How long does it take 80% of a sample to decay? Okay, R equals R naught times 2 to the negative T over H. If 80% of the samples decayed away, then 0.20 R naught is how much remains. That equals R naught times 2 to the negative T over 18.4 days. So R naught cancels, 0.2 equals 2 to the negative T over 18.4. Taking log base 2 of 0.20 equals negative T over 18.4. So transposing the 18.4 on the negative side, T equals negative 18.4 log base 2 of 0.20. Now, okay, for this, we use the change of base formula and write this log base 2 as common log over log 2. So T equals negative 18.4, common log of 0.2 over common log of 2. And a bit of calculation later, that's 42.7 days. Carbon-14, carbon dating. Carbon-14 is naturally generated in Earth's higher atmosphere by cosmic rays. Then it settles down into the ecosystem and gets incorporated in basically every living thing. So we're all mildly radioactive. Now, when an animal dies, and of course stops eating, it stops taking up carbon-14, and this carbon-14 slowly decays away. So it goes for bone, it goes for leather, it goes for wood, and so on. So here we have a bone fragment. But 60% of its initial carbon-14 remains. How old is it? Carbon-14 has a half-life of 5,700 years about. Okay, we use the radioactivity formula. Radioactivity equals initial radioactivity times 2 to the negative T over H. Here we have 60% of the initial radioactivity remains, 0.6 R naught, equals R naught times 2 to the negative T over H is 5,700. So we want to solve for T in this equation. As ever, R naught cancels. Radioactivity doesn't care about how much initial was. So 0.6 equals 2 to the negative T over 5,700. Taking a log base 2, get log base 2 of 0.6 equals negative T over 5,700. Transpose the 5,700 into the negative, get T equals negative 5,700 log base 2 of 0.6. Log base 2 of 0.6 we rewrite as common log of 0.6 over common log of 2. So T equals negative 5,700 common log of 0.6 over common log of 2, and a bit of calculation gets you about 4,200 years. Now here we have the pH of a solution is a hydrogen ion, well really hydronium ion, concentration of 1.7 times 10 to the negative 5th. That's easy. You take minus the common log of 1.7 times 10 to the negative fifth. That's a pH of about 4.77. Fairly acidic. Now here we have a Newton's cooling law. This is where it gets complicated. A cup of tea is poured boiling at 212 Fahrenheit in a room with temperature 70 Fahrenheit and cools to 120 degrees in 10 minutes. Assuming Newton's law of cooling, when will it be 90 degrees Fahrenheit? What temperature will be a half hour after pouring? Okay, this is a bunch of stuff happens. So here we go. T naught equals 212. TS, the surroundings, is 70. D naught, the difference between these two, 212 and 70, is 142. And T at 10 minutes is 120. So we're told. So, well, all right, here we use the formula I mentioned up above. T of T equals 70, the stable population, plus 142, the difference, times, here it gets a little complicated. 120 minus 70, T at 10 minus T of S, over T naught 212 minus T of S, 212 minus 70, under 120 minus 70, all of the T over 10. And all right, so you get approximately 70 times 142 times 0.3521 to the T over 10. So after a bit of calculation, K equals negative common log of 0.3521, which is about 1.044. So the time is 10 natural log of 142 over T of T minus 70 over 1.044. So when the temperature at time T is 90, the time is natural log 142 over 90 minus 70 over 1.044. After a bit of calculation, that's 19.7. So the 90 degree T is in 19.17 degrees. T at 30, just plug in 30 into the formula that we had here. So 70 plus 142 times 0.3521 over to the power 30 over 10, 76 over 2, 0.2. So it's 76.2 Fahrenheit degrees T in 30 minutes. All right, so it all comes down to these rather gnarly formulas here and here. That's why I assigned the Newton's problem, cooling problem, as an extra credit in the homework. All right, so there's that for that.